law problem. We're talking about this. How do you know which type of problem? Here I asked you for delta G, delta H, delta S. I gave you the reaction. Here's a table of delta G's, delta H's, and as advertised, I left some blank spaces. How about that? And the thing you know is, this must be a 0, this must be a 0. What's this? Some number. You don't know what it is till you calculate it. But somebody, did I hear somebody say negative? Nah, it has to be positive, right? Because those are absolute values for entropy. What's the smallest absolute value for entropy you can get? 0. Where do you get 0? At absolute 0, or at 0 kelvins, right? Okay. Oh, one other thing I just wanted to mention here, because I saw the electrochemistry. What does delta G mean? It can calculate it by doing these combinations of entropy and enthalpy, but the other thing we talk about when we talk about the free energy change for a reaction, it represents the maximum amount of work you can get from the reacting system. And the reason I mention that, because I'll come back and say that when we get to electrochemistry, but delta G since I want it to be equal to a standard state, it's W max when you're working at a pressure of 1 atmosphere, molar concentrations of 1. So if you can get the maximum amount of work from the system, that would be equal to delta G. And I drew that pressure volume graph a day or two ago, and I said as you do smaller and smaller steps, eventually you can do the work reversibly, and that gives you the maximum amount of work from the system. REV for reversible. And when I looked at this problem, that's the next step. That's the next thing we're going to do after the exam. We're going to relate cell potentials to reversible work, or delta G. Okay. So I just tossed this in right now while we're talking about free energy change, but I'll come back to it again in the near future, sometime after this. Okay, coming back to this problem now. Notice I can calculate delta H, because I know this is the product. There's 1 mole of it. So I have 1 times this, minus 1 times this, minus 0. That's a plus sign. What's that? So that's a 2 plus. If I would have made these 2, 1, and 2, then this thing would have said what? 2 times this, minus 2 times this, minus 2 times, minus 1 times 0. Doesn't matter, it's still 0. I can calculate delta G. Okay? 1 times this, minus 1 times this, minus 0, gives me delta G. Says what's delta S? Can I erase all this? Yes, you're all up, right? But I also told you where you can find this, because this is the equation we're going to use. Notice when I calculate these two things right here, when I calculate delta H0, delta G0, I can immediately tell whether the reaction is exothermic or spontaneous or whatever. want to calculate S. Notice I said I want you to fill in not S0. I mean not, I didn't say. Sometimes I tell you no. But I want you to calculate delta S. What you're solving is for this quantity. And this is where people have trouble with their algebra. Right? Wrong? Right? Wrong? The reason I keep saying that is because I always see people doing delta G minus delta H over T. Or delta S. Make sure you do the algebra. So I plug in these numbers right here and solve it, and it's going to come out in. And the reason it's going to come out in kilojoules because these numbers are all in kilojoules. Now the next problem is it says fill in this blank. What I have to do is say delta S0, and I have to change this one to joules per Kelvin because these are in joules per Kelvin. So I get this number from here by shifting the decimal point, and it's equal to I solve for x. And I'll have the number that goes in here. That's going to be a positive number. Oh, and by the way, lots of times when you do a bunch of these problems, the book he always does oxygen, and he comes out to 205.0 every time because that's what's in the table. What happens is when I give you these numbers, I change the decimal point, the numbers after the decimal a little bit. And you don't get 205.0, you have to get some other numbers, so make sure you calculate them. Don't remember it. And I can do the last problem. Because I have delta G. It's going to be a case of P. That's also, when I wrote that delta G0, he pointed out that is what is called the thermodynamic equilibrium constant. When we're working with gases, okay, these are all gases, then it's going to be case of P, and case of P is the thermodynamic equilibrium constant. The only time this differs from the equilibrium constants we're used to working with is if you have a reaction like, oh, let me think. Whoops, H2O. Now, when we talk about our normal equilibrium constants, if that's H2O liquid, we don't bother putting it into the equilibrium expression, right? But when we talk about the thermodynamic equilibrium constants, we have to use delta H for this, or delta G for this, and delta G for this, and delta G for each of these other things. Then the thermodynamic equilibrium constant is not equal to what we call the different equilibrium constants because we leave some things out when we're doing our shortcut. Okay? In other words, let me write a net ions equation here. CaO solid plus 2H plus, what happened to my lights? In other words, this is the net ionic equation. This is a solid, so when I write the equilibrium expression, this exercise. This is what we would get for our equilibrium expression in what we usually do. Okay? But this is not the same as the thermodynamic equilibrium expression, because you had to use delta G for this, delta G for this, delta G for this, and delta G for this. So the thermodynamic equilibrium constant, thermodynamic equilibrium expression would have all four of those in. And I don't really want to write it like that. These two things would have to be included as part of the thermodynamic equilibrium constant. Because when we calculate this delta G for this, we have to put in the delta G0 or delta G sub F for calcium oxide. We have to put in the delta G sub F for H2O liquid. And how many times have we done an equilibrium like this? None. We aren't going to at all. But that's the distinction he makes, because somewhere in one of the problems I gave you, he says, is this an equilibrium constant? Is this a thermodynamic equilibrium constant? You write the normal thing. For this thing here, these were all gases. My normal equilibrium expression would be that's PO2, I just ran out of space. And this is what my equilibrium expression would be. That's what my thermodynamic equilibrium expression is, because I put all of those things into the equilibrium expression in pressure units. Okay. So he makes a big deal about the difference between the thermodynamic, well, he does. He makes a big difference between the thermodynamic equilibrium constant and all the equilibrium constants we've been working with in the equilibrium chapter. And the big difference is we left out some of the things, we left out solids, we left out the liquids and things like that, which if you're doing the thermodynamic equilibrium constant have to be included, because you use those free energy changes for the different substances in the balanced equation to calculate the overall free energy change. But for this one, we use the free energy changes for all of those. All of those appear in our usual equilibrium constant. Then the next question, somebody says, if I'm doing that calculation, what should I use for my R? Is that the next question? It's not. The answer is, when you look at the data, if they give you pressure units in atmospheres, you're going to use the 0821 number. If he updated that problem or those problems in this textbook, and I don't think he has, then he'll give the pressure in bars, then you use the 0831 number. That's all. And I think all of his problems are still with the old pressure units in atmospheres rather than the new pressure units in bars. So we're all the way up to where I will be on the exam. I'll talk about temperature effects for equilibrium before the exam, or yeah, because we'll do the exam the same way we always do. We'll do some lecture, answer questions, and then we'll do the exam. Okay. So if there are no other questions, I'm also scheduled to start the pre-lab for Lab 4. It's no use doing that because nobody's picked up the unknown for Lab 3 yet. Hopefully everybody's going to be started on Lab 2 unknown today, and if not, by about a half hour into the lab work, show me what you have. We're going to have to move on. Otherwise, you'll still be doing Lab 2, and the rest of us will be taking the final exam. that means we won't get any more labs done than number 2. Okay. Any other questions?